Okay, this morning we're going to try a couple of additional examples. These are applied extreme value problems. This is question 39 from the textbook. It says, for raising a load, the efficiency as a percentage of a screw with square threads is given by, and we have an equation. F is the coefficient of friction, and T is the tangent of the pitch angle. When F is 0.25, what acute angle makes E the greatest? So we're trying to maximize the efficiency of the screw in this problem. We're asked to omit the second derivative test, and this is largely because it would involve way too much work. All right, so let's begin. We should determine what we're trying to maximize or minimize. Okay, so again, it's the efficiency, E, that we're trying to maximize. And we're looking for the acute angle that makes this happen. But when you look at the equation, it doesn't directly involve the angle. But what it does involve is the tangent T of that angle. So really, what we're going to do is determine capital T such that E is a maximum. So here's our goal. We're going to find the value of capital T such that capital E is a maximum. Okay, so we are going to begin with the equation given. Except that there is one other letter involved in this equation, and it's little f. Little f can be treated as a constant, and in fact it's given to be the number 0.25. That's the coefficient of friction. So I'm going to substitute that here as well. All right, like that. So that's much better in that now the equation involves only the variables T and E. So that's a good step. Now, how is it that we look to maximize the efficiency? What we're going to be doing, so this is our plan. We're going to be taking the derivative of efficiency with respect to that tangent, and we're going to be setting it equal to 0. And then we're going to solve for capital T. So this is our plan. And if we were going to include the second derivative test, we would also look at d squared E over dt squared, and we would ensure that it is less than 0, guaranteeing a maximum. But since we are omitting the second derivative test, all we need to do is this portion. Take the derivative, set it equal to 0, and solve for capital T. All right, so if I'm going to take the derivative of something like this, I can see that capital T is in the numerator and the denominator. So I am going to use the quotient rule, but in the numerator right now, it looks like a product as well, because we have one function of T here and another function of T here. So to make this much, much easier to work with, we should just open up this bracket using multiplication. So now the numerator instead Oops. The numerator instead will look like this. Okay, so we're going to get in the numerator 100t minus 25t squared. And the denominator here remains the same. All right, so again, I just opened up this bracket here, and of course we can do that because the exponent here is just a 1. All right, perfect. And now I do still have a quotient. The variable t is in the top and the bottom of this fraction. So this is when we call the top u and we call the bottom v, and we form our u prime and our v prime, and then we substitute into the quotient rule. Okay, so what are we going to use for u prime? We're taking the derivative with respect to the variable t. So it'll be 100 minus 50t. And what are we going to use for v prime? The derivative of t plus a quarter is just 1. So now we have u prime and v prime. So we can find the derivative of e with respect to t by using the quotient rule. So I think I'll put my line in first here. All right, so how does the quotient rule go? It is v times u prime minus u times v prime over v squared. Okay, so that's the derivative of u over v. So here we go, v times u prime minus u times v prime over v squared will look like that. And now we just have to carry out the algebra implied. So I think I'll leave the bottom just like this, but in the top here, let's multiply these two binomials together, and then let's multiply this binomial by -1. Okay, so when we multiply the two binomials together, of course we have to do first outside, inside, and last. Okay, like this. First, outside, inside, last. And I got those 4 terms. And now here we're bringing -1 inside, so this will be -100t and positive 25t squared, like that. Okay, so now let's collect our like terms in that numerator. Okay, so collection of like terms now. So these two terms are like terms. So we will have -25t squared. And these 3 terms are like terms. So we have 100t, -12.5t, and -100t. So that's -12.5t. And then the constant plus 25. Okay, so that is correct for the derivative of e with respect to t. And the key is we're looking for places in the graph that are extremes, which means that the slope of the tangent line will be 0 at those extremes. So we're setting this equal to 0. Now, the only way for this expression to equal 0 is if the numerator is equal to 0. So the denominator here can simply be multiplied by 0 on the left. So now we just have this. right. And this is a quadratic equation. In fact, this one is not factorable, so I'm going to use the quadratic formula on this in order to solve for t. And so using the quadratic formula, of course, I have A is negative 25, B is negative 12.5, and C is 25. And so I plug into the quadratic formula to find t. So you know how this goes, negative B, so that'll be positive 12.5, plus or minus the square root of, now we do b squared minus 4ac. B squared minus 4ac. So here's my calculator. Okay, oopsie, there we go. So negative 12.5 squared. So you see we have to actually put a bracket since it's a negative number. My button there is sticky. Okay, here we go. So negative 12.5 in a bracket squared, that's b squared, minus 4 times a is negative 25 times c is 25. So underneath my square root sign, I have that number right there. 2656.25. That's the discriminant. We call that number the discriminant. And then we have to divide this by 2 times a, and that's negative 50. And then we can solve for t. And of course, we get 2 different values at this point in time. Clear that. All right, so 12.5 plus the square root of this number, 2656.25, is that divided by negative 50. So here's one answer, negative 1.28-ish, okay? Blah, blah, blah. Can I just do that? Blah, blah, blah. Or, and now we'll get the second answer. 12.5 minus the square root of 2656.25 is this, divided by negative 50, and we get this answer, 0.78-ish. Right? Dot, 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 dot. Okay. This is the answer I want to use. How do I know that? Because remember what t represents. It's the tangent of the pitch angle. And the angle is acute. So the angle is in quadrant 1. The angle's between 0 and 90 degrees, which makes sense if it's the pitch angle of a screw. So the angle is acute, which means that the tangent of the angle is positive. Remember that for every quadrant 1 angle, all the trig functions are positive. So this is not the answer that we want. This is the answer that we want. This guy right here on the calculator. But is this the answer to the question? Remember, this is the correct tangent of the pitch angle to maximize the efficiency, but the question says, what is the angle? So what we know is that theta, therefore, is going to be the tangent inverse of this number. Okay, so we have to do shift, tangent, and right there we get our angle, and it's, oopsie, you know what, I'm in radians. So I should be in degrees. I mean, let me just do that again. Okay, sorry, I just switched my calculator to degrees. I think it'll be more meaningful to you if it's in degrees, that's all. So let me just try that again. So I want to put the answer back in here. I think I've lost it. Yeah. Okay, 12.5 minus the square root of 2656.25 is that divided by negative 50. Okay, so my answer is back. So now I'm going to do shift tangent equals, and there we go. That's the angle there. It's roughly 38 degrees. Okay, and now we're finished with the question. All right, so again, we had an equation that involved only two variables because F was given and it is constant. The coefficient of friction is a constant. So we were able to substitute that right away, and then we had an equation that only involved E and T. So naturally, we took its derivative. I mean, it is a calculus course. So we began by taking the derivative. And the key is after you take the derivative, set it equal to 0 and solve for the variable. Okay, set the derivative equal to 0, solve for the one and only variable. And one little trick in this question, the question wasn't asking us for t, the tangent of the pitch angle. It wanted us to find the actual angle. So we had to finish the problem just with the tangent inverse of our answer. Okay? All right, let's do one further example together. So the last one we're going to do together is question 52. So let's read through this and attempt to solve it. So a cylindrical cup, so there's no top on it, okay? And it's a perfect cylinder. So you're picturing a cup that's a perfect cylinder. It's designed to hold 375 cubic centimeters or 375 milliliters. There is no waste in the material used for the sides. Okay, so the sides are made such that no material is wasted. However, there is waste in that the bottom is made from a square 2r on a side. Okay, so that probably requires a little bit of explanation. What are the most economical dimensions for a cup made under these situations? Okay, let's talk about the cup. So when you make the sides of a cylinder, it starts with a rectangle. So I think you guys know that, being mechanical students, but I will show you what I'm talking about here, right? So pretend that that's a perfect rectangle. So if you have that rectangle and you roll it up, that's how you make your cup, right? You simply take the rectangle and roll it up such that it makes what we're calling the sides of the cup. So what would be the dimensions of this? Well, the dimension here would be the height, right? The height of the cup. And what about this side length? Well, when you roll this up, this makes a circle, and its dimension is the circle circumference. Okay, so what you're doing is you're rolling up the cup. This is the height of the cup, and 2 pi r, which is the circumference of the circle, is also the width of this rectangle. Okay, so that's how you're making the cup sides. Okay, so when they're calling something side here, right? There's no waste in the material used for the sides. Okay, so this is for what we're calling the sides. Okay, however, there is waste regarding how the bottom of the cup is made. So here's what they're saying for the bottom of their cup. They're saying that they're taking a square. So I'm attempting to draw a square here. And this isn't obviously to scale. Okay, but anyway, they're taking a square. They said it's 2r on a side. What that means is it's a 2r by 2r square. And they're using that to make the bottom, so that's for the bottom of the cup. Remember, there is no top. So what they're doing, you see how you can get some waste from there? They're cutting out a circle from that piece and throwing away the little bits. So if I had any drawing ability at all, I would draw for you a perfect circle in here. Okay, and I would show you that these little extra bits here, these are what they're calling the waste. They throw those out. So they're cutting a circle out from the square. Okay? Okay, and of course, yeah, in that way, there's little scrap pieces here that are getting thrown out. Okay, so now we want the most economical dimensions, and of course, that will result when we have the minimum area. Okay, so we are supposed to find the dimensions. So in other words, determine H and R such that the area will be minimized. So the total amount of area, in other words, the total amount of material. So let's write an equation for the amount of material we're using to make one of these cups. So for the sides, it's just the area of the rectangle. So 2 pi r h. And then for the bottom, it's the area of this square. So it's 2r multiplied by 2r, which is the same, of course, as 4r squared. Okay, so it's 2r multiplied by 2r. And that, of course, is the same as 4r squared. So here is our area equation. And this is what we are trying to minimize. Now, the issue with this equation, of course, is that in the right side are two different variables. Neither of these things is a constant. The r isn't constant, the h isn't constant. So before we begin with our derivative, we have to eliminate one of these variables. Well, how are we going to do that? We can use this fact. The cup will hold 375 cubic centimeters. Well, that is giving us the volume. What is the volume of this cup made? Well, its volume is given by the area of the base of the cup multiplied by its height. So what will the area of the base be? Of the cup though, right? So that means once these little scraps are thrown out, we have the bottom. What would its area be? Its area is pi r squared. So the volume of the cup is pi r squared h. You might have known this as the volume of a cylinder. Pi r squared h, therefore, is 375. And if you didn't know pi r squared h was the volume of a cylinder, again, it's the area of the base, which is a circle, multiplied by the height. And don't forget, inside the front cover of your textbook are many, many helpful formulas as well. Okay, so this is very helpful to us because we can isolate h from this equation, and then we will have an equation only with r's in it. So what I mean is that from this equation, we can see that h is 375 divided by pi r squared. And that can be substituted right here in the equation. So the equation becomes 2 pi r times 375 divided by pi r squared plus 4r squared. We can simplify this quite a bit. Okay, so pi will cancel. And one of these r's will cancel as well. So we're going to get 750 over r plus 4r squared. Okay, so we can do this as well, show that 1r will cancel. So then we get 2 times 375 over r plus 4r squared. And since we're going to be doing some differentiation, we know it's preferable to write it this way. 750 times r to the negative 1 plus 4r squared. Okay, so now what was our objective again? Well, we are going to determine r, the radius, such that a is minimized. So how is that done? That's done by taking the derivative of a with respect to r, setting it equal to 0. We will then solve for the radius r, and we can guarantee or show that at this value of r, the second derivative, d squared a by dr squared, is greater than 0. So this is our plan of action now to solve this problem. Okay, so let's execute it. We're going to take the derivative of this and set it equal to 0. So what is the derivative? Well, we will get negative 750 r to the negative 2 plus 8r. So that's what we're going to set equal to 0. So we're going to get 0 is, now we should maybe write it negative 750 over r squared plus 8r. Maybe that'll help us. You might remember in our last video, I used this trick where we cleared out the denominators after this step. So we can multiply all the terms by r squared here. And that would be 0 equals negative 750 plus 8r cubed. So that's what you get if you multiply this term, and this term by r squared. Now, solving for r, we just want to isolate r. So we're going to get 750 is 8r cubed, or 8r cubed is 750, which means r cubed is 750 divided by 8, or 93.75. And so r is found by taking the cube root of this. So we want to do the cube root of 93.75. So that is roughly the radius, approximately 4.54 centimeters. Like that. And so remember, once we have the radius, we should also determine the height, okay? Because the question asks for both dimensions. So we just would take this height value and maybe substitute it right here into this equation in order to figure out that height. So we're doing 375 divided by pi time, so this, look how I wrote this. This isn't good. That was r cubed, and this should say r is roughly 4.54 centimeters. Sorry. R cubed is that, and R was roughly 4.54. 4.54 centimeters. Okay, and then once we have that R, we simply substitute it into this equation for H, and we'll get that H is roughly 5.78 centimeters. Okay, so, and that's just by doing 375 divided by pi times 4.54 all squared. And now we have the height as well. Okay, so we took the derivative, set it equal to 0. We solved for the radius, and then in turn for the height. And now, can we do the second derivative test? Here's the first derivative. I think I have just enough room to include it here. What is the second derivative? So we just take the derivative of the first derivative, and then that will be negative 750 times negative 2r to the negative 3 plus 8. So this is positive 1500 r to the negative 3 plus 8. Which is the same as 1500 over r cubed plus 8. And when r is a positive number, this, of course, is going to be positive. All right, if you want to know exactly what this is equal to, we can work it out. It's 1500 over r cubed, so it's 1500 over 93.75. So 1500 divided by 93.75 is that plus 8. Okay, so it's actually equal to 24. The second derivative at this radius value is exactly 24. We don't care about the numeric value, but we do care that it is greater than 0, which confirms that we have found the radius value that does provide for a minimum amount of material. Okay, so that's 5 examples that I presented in total on this topic. I have made some suggestions for you in Blackboard as to which problems you should try. And not only that, but I have posted full solutions for you in Blackboard for those problems. So please, I know this isn't an easy topic right here. These word problems can be a little difficult. So please take the time required to review and go over all of those problems. Okay, thanks a lot. Have a good day.